So this video is going to be a little bit of a different format, because I think the easiest way to understand this is to look at some actual work that's being done. So people are still measuring absolute entropies and other thermodynamic functions of new materials that are being made. And so I went to the Journal of Chemical Thermodynamics, a peer-reviewed journal that you can find online. We have access to it through our library here at Connecticut College. And this just happened to be the first paper I grabbed. So this is something published this year in 2021, looking at heat capacity and thermodynamic functions of these zeolites, right? So this is a material that you can make with some cation exchange, right? So different things trapped into it. So zeolites are materials that have like atomic or molecular sized holes in them that can fit in like these cations. I thought it was interesting that this is actually from my alma mater. So I went to Brigham Young University, and I had Dr. Woodfield here, Brian Woodfield. He taught one of my general chemistry classes. So kind of fun to see an article published by a former professor of mine. And he worked on thermodynamics, right? He was a physical chemist who worked on thermodynamics. So he and his group and some other people from Arizona were able to do this, to make this the substance and then characterize its thermodynamic properties. So if we scroll down a little ways, we'll skip past the abstract. So just to show sort of what this looks like, all right, we have these spaces here inside the zeolite that have different can have different cations in them, and that's what we're looking at here. Okay, so but what we're looking at is the experimental section. They describe, they synthesize it according to a procedure that was described somewhere else, et cetera, et cetera, et cetera. So the part we're interested in is they did a thermogravimetric analysis, so that's TGA. So that's measuring as you heat it up, does water evaporate off of it? We can measure that, and so this is like their experimental data here. But what we're interested in here is heat capacity measurements, because that's what we need in order to calculate entropies. So heat capacity measurements were performed with a quantum design physical property measurement system in zero magnetic field from 1.8 to 300 Kelvin. So the first thing you may notice here is that you can't start at absolute zero, of course. So you have to start at a temperature slightly above absolute zero. Still very cold, right? Only 2 Kelvin or so. And so you can do this using liquid helium and things like that to get your substance down to this. And so we'll talk a little bit about how you get that part that's not in there, right? The 0 to 1.8 Kelvin. Everything else you can measure the heat capacity using this thing. So then they put about 10 milligrams of the sample into their copper cup with a small copper coil, also inserted to ensure uniform heating throughout the sample, and then they measure it. They heat it up slowly, and we're able to measure the heat capacity. As they put in energy using this copper, right? They put in a known amount of energy and measured how much did the temperature go up. And through that, you can measure the heat capacity, and then you do that as you keep increasing the temperature, and that gives you this function that we can then integrate to find absolute entropies. So if we go down here, this is their heat capacity as a function of temperature. And so this is their actual data for different cations inside of their zeolite crystal. They show at the low temperature range down here, where you start close to zero heat capacity, and then it starts to increase. And then they do the range all the way up to room temperature. And what you can see here is that this stays solid the whole way, right? This is a crystal of some kind, and so we don't see any big jumps that you would associate with a phase transition, right? So this isn't melting or vaporizing, and so this one's a little bit more straightforward. We can just fit this data to, say, a polynomial function or something else, integrate it, and find our entropies that way after dividing by temperature. So this then just shows what the individual values that are in all these points here. And using that, you can calculate the entropy. All right, this is just the different. So there's their data fitting here. They have there's a standard way to fit this, and then standard thermodynamic functions, right? So then what we're looking at here is what's the entropy, and so then you can integrate this heat capacity as function temperature, integrate it to get the absolute entropy. And so this column right here is what we're interested in. And you can, of course, integrate up to different temperatures and get different values. So just to show you an example of how you could actually use that. This is in experiments that are done this year to be able to get this information about substances that new substances that we're making all the time.